Hi there, this is Mr. Sand, and I'm going to talk to you today about effective nuclear charge. So let's start this off with a positive nucleus. Here's a positive nucleus. It's got one proton, and let's say it's got two protons, maybe three protons. Okay. And it's also got its neutrons. I'll draw those in as well. One, two, three. There's neutrons. And then I'll just draw on the shells where the electrons could be. There's a shell. And I'll just do two shells here. All right. Now, on for the electrons. So this is lithium. It has three electrons. I'll put one right there. I'll put another right there. And I'll put the last one out here. Okay. Now, effective nuclear charge is defined like this. It's the charge that a particular electron, I'll put in quotes here, feels. It's given to you with this formula, and I'll just write the formula out right here. It's like this. It's kind of weird. ZF is Z minus S. ZF is just the same thing. It is effective nuclear charge. Z, I'll write that in red. That makes the most sense to be in red because it's the number of protons. Number of protons. And S, well, S, it does make sense that it's in blue or this teal color. It's the number of electrons, this is the weird part, that are inside, quote, inside the electron you are considering. So let's just say, and I'll tell you the main idea of this is that you can think of this kind of, it doesn't quite work all the time, but this could work, I guess, if you need to think about it like this. Think of this central positive charge as like this warm campfire. It's nice and warm. And around this campfire, you've got these electrons, which are like people. Okay. You are closer to the campfire. You're warm. You're basking in the warmth and it's so nice and warm. On a cool evening, let's say it's a really cold evening, all you want to do is stay warm. So you get up close to the campfire and you stare into the flames of the campfire. It feels great. But if you don't get the prime real estate right next to the fire, you're relegated to having a spot that's farther back. And so you don't get to bask in as much warmth that these people up front get to bask in. They get the full glory of the nucleus and the positive charge here. So they're really attracted to this. Now I'm going back into my electron description here. They're very attracted to this nucleus here. This electron over here, since it's being blocked and it's farther away, it does not feel the same pull towards the nucleus as these guys do. So if you want to draw relative pull, it'd be something like this. Pull. So this would have very strong, I'm going to make a big arrow, and this would be a relatively weak arrow compared to those big, strong arrows being pulled towards the nucleus. Okay, so these electrons would have greater effective nuclear charge than this electron out here, this poor soul that's stuck on the outside. Oh, poor electron. So that's the main idea, is that the closer you are, the more effective nuclear charge you have as an electron. So the further out you go, the less effective nuclear charge this electron has, and the less attraction it has to its own nucleus. So you can start thinking, okay, maybe if it has less attraction over here, it's easier to be knocked off. And that's true, it is easier to be knocked off. For lots of other reasons, it's easier to be, for lots of other events, it can be knocked off easier than these. These are held tight. They're very close inside, close to this nucleus. Okay, I think I've gotten that covered. So let's go back to this formula here for effective nuclear charge. We've got ZF equals Z minus S. Z is the number of protons. In this case, for this atom right here, well, first let's choose one of these electrons. If we choose these electrons, it's going to have a different effective nuclear charge than this. Let's choose the inner electrons here. Let's choose this guy. This is our guy I'm going to calculate effective nuclear charge for right now. So my ZF for this guy is going to be the number of protons. I'll switch to red. That's 3 minus the number of electrons inside the electron you're considering. So in this case, are there any electrons inside here? No, it's the closest one. So it's going to be 3 minus 0. So it's Z effective, or the effective nuclear charge here for this electron that I just starred. That electron is going to have an effective nuclear charge of 3. Now let's take a look at this electron outside. Let's erase this little star. I'm going to erase it like that. Great. So now this effective nuclear charge for this guy over here. Now the number of protons, that's stayed the same. 3. How many electrons are inside this electron that we're considering? There are 2 inside, inner to this electron. Sometimes they call it core electrons. Electrons that are core to this electron. So these electrons are core to that electron. So I would have to say that there are 2 electrons. There are 2 electrons. So the overall effective nuclear charge for this is going to be 1. So for these electrons, their effective nuclear charge is 3. It's a bigger number than this on the outside, and that makes sense. Okay, that should make sense to you as well. If you've got bigger atoms with more electrons, then you just have to consider the electrons that are inside of them. It's pretty easy. This calculation is not that hard. It's just the overall concept to think that if you've got an inner electron, it's going to have more of a tug towards the nucleus than the outside electrons. And that's a good explanatory tool that you'll use later on with periodic trends. We're going to get to that in a minute. Okay, that's it for me. Good luck on your problems. Bye.